Basic electronics. This is the last topic for S3 physics. Just like all the other topics we've done at S3, this is going to have some very strong links to the National 5 course. Where these links are of particular importance, I'll try and flag those up for you. So those of you who are going on to Nat 5, keep a wee eye out for moments like that and keep that information in mind for next year. But let's get started. So when we're thinking of basic electronics, what we're normally thinking of are electronic systems. Electronic systems are everywhere. We're using them all day long, and pretty much everything we use now has got one or more electronic systems in it. The computer I'm using to record this, the phone or laptop you're watching it on, they're all electronic systems. They're very complicated ones, but they're electronic systems. Though all electronic systems, no matter how complicated or how simple they are, have something in common, and that is that every electronic system is made up of three parts. These three parts are the input, the process, and the output of the system. If we want to show this in a wee diagram, if you're talking about particular inputs and outputs, we do a little block diagram like this. You have your inputs here, then they are processed in some way here in the middle, and then after that process is happening, your system gives you something at the end. So it outputs something useful at the end of the system. What we're going to do now then is have a wee look at those individual three steps, those three parts in a little bit more detail. Let's start with input devices. There's a whole range of input devices, but what they all do is they take a form of energy, could be any type of energy, light, sound, kinetic, chemical, and they change that into electrical energy. The reason they change it into electrical energy is so that it can be used in a circuit or a computer system. Okay? Examples of these are things like microphones and switches. Let's concentrate on the microphones for now. Right now, as I record this, okay, I'm using a microphone. That microphone is picking up all the sound energy of me waffling on through this presentation, and then the microphone changes that sound energy into electrical energy that the computer can save. So the computer by itself wouldn't have been able to do anything with the sound energy, but once it's changed into electrical energy by the microphone, there's loads of things it can do with it. Okay? Switches, they're taking a little bit of energy from you turning a switch on or off, and they're turning that into electrical energy to turn on something else or turn off something else. Solar panels, they're taking light energy from the sun and they're changing that into electrical energy to power houses, sometimes power whole cities. Okay, these two at the bottom, a thermistor and an LDR, we will talk about those in a little bit more detail later, but this is the first of the things that's going to come up a lot more at National 5 because they're more complicated input devices. Right, next let's look at the process devices. So this is the middle of your three parts to an electronic system. So what a process device does is it takes that electrical energy, that signal from the input device, and it does something to it. It acts on it in some way. Now, there's a whole range of different process devices, so it can act on this electrical energy in a whole range of different ways. And the way you want it to act on it obviously depends on what you want your system to do. We're not going to look at any in particular process devices, that's a bit beyond us at this point, but some of the things it can do, like changing the signal to something more useful. It could count the number of times it's getting a signal or the number of times something is happening in the signal. It could introduce a time delay to it. It could even, if you've got some very impressive process devices, make decisions based on those signals. Now, let's start looking now at output devices. For us, these are probably the most exciting, okay? These are the ones that actually do something, okay? Actually get something fun, or useful at least, from an output device. What these do is, they take that electrical energy that was created by the input device and processed in some way, and they change it into a useful form of energy. Most of the time, we as humans don't actually need this electrical energy. It's not useful to us. What we need is light energy or sound energy. And so an output device gives us that. Examples of that then are things like loudspeakers, electric motors, lamps. Let's look at this one here, okay, loudspeaker. This is something you should all be using right now. Whether you're listening to this through the speakers on your laptop or phone or through headphones, there's some sort of speaker system involved. And what that speaker is doing is it's taking the electrical energy from inside your computer, and then that's changing that into sound energy that you can hear, unfortunately. Okay? An electric motor changes the electrical energy into movement energy to power things. Lamps and heaters change it into light and heat. Again, light and heat much more useful for us in most situations. Okay. Again, there's a couple of things here, relay, solenoids and LEDs, that we'll look at a bit more if you progress on to National 5. Okay. Now, let's have a wee think about an electronic system as a whole then. Now we know what those individual parts of it are. Let's think of the electronic system being used here for me to record this and share it with you. The input device is at my end of the system, and that's a microphone I'm using. That microphone is taking the sound from me and it's changing that into electrical signals. Process device is then being used. It's tuning that electrical signals, it's amplifying it, maybe it's saving it somewhere, doing a lot of different things to it. Then the output device is at your end. The loudspeaker is then using that processed electronic energy and turning it into sound energy again, so you can hear me. So even though it started off as sound energy and it finished as sound energy, quite a lot has happened in between. Okay, and that's what the processes did. What we want to look at now then is we want to zoom in a little bit. Instead of thinking of the electronic systems as a whole, we want to look in more detail as to what actually makes those up. How are these powered? How does the electricity involved actually work? What we're going to do for the start of that then is we're going to have a little recap of some stuff you should have covered in S1, S2. If you've forgotten it, nothing wrong with that. This should remind you of everything you need to know. And so the first thing we're going to look at then is some basic terms when we're dealing with electricity. The first of those terms is current. You're probably familiar with the word current. Okay, if you're thinking of a river or pipes, the current is the water flowing through them. It's very similar when we're dealing with electronics. The current, instead of us thinking of the water flowing, we think of electrons flowing. You talked about electrons previously, and you should know that electrons are very tiny particles that have a negative electric charge, and that's what's flowing through the wire. So if we're being more technical, and you'll need to know this for going on to Nat 5, instead of thinking just of current as the flow of these electrons, we can think of it as the flow of charge through the circuit. So because each of these electrons has a charge, that charge is moving around the circuit, and that's what the current is. Okay, it's that charge moving around. Next thing we're going to look at, the next term we'll remind ourselves of, is voltage. This is the biggie for electric systems. Okay, voltage, we can think of that as the amount of energy that these electrons are given. The higher the voltage, the more push these electrons are getting to go around the circuit. The lower the voltage, the less push they're getting. Then finally, that takes us on to resistance. Okay, so as you'd guess from the name, the resistance of a circuit is whatever's pushing back against that flow. Okay, so a resistor is a specific component which opposes or resists the flow of charge. Sometimes the voltage is too high and there's too much push being given to the electrons, and so we put a resistor in to push back against that flow, slow it down a bit, reduce the energy. Now, this picture you probably recognise, it's up on the wall in the physics classroom, so you've no doubt seen it before, but you may not have paid much attention to it. This is just a fun wee diagram to show what's actually happening, or to help you visualise it. So here we've got our volts, and they're pushing the amps. We'll come on to this in a second, but amps is another word for current. They're pushing that current through the circuit. Our ohms here, which again on the next slide you'll see is another word for resistance, that's trying to stop this being pushed. It's tightening the circuit here to try and push back against and oppose this current being pushed through the circuit. But unfortunately in physics, obviously, we can't think of things all the time in little cartoons. We need to do equations and stuff with it. And to do equations, we need units. And that's what we're going to look at next, okay? And that's what these ohms here and the amps here are. Because remember, in physics, your units are just as important as your answer. So if we want to look at these and how we use current, resistance, voltage and charge actually in equations, so we can work things out in a little bit more detail, we need to know what the symbols for them are in our equations and what the units are for them in our answers. So let's start with current. The symbol for current, when you use it in equations, is a capital I. It's measured in amps, and the units for that are a capital A. For voltage, the symbol for that, a bit easier to remember, is a capital V, and the units for that are volts, and again, we just use a capital V, okay, in your answer. Resistance, nice and easy for the symbol, capital R. Units are a wee bit trickier. The units are ohms, and then we use this symbol here, which is from the Greek alphabet there. So if you're giving an answer to a question where it's asked you what is the resistance, your answer should be a number followed by this little symbol here. Then we'll just cover this quickly. Charge, which we talked about before, which electrons and the current has. The symbol for charge in an equation is a capital Q, and the units for in your answer are coulombs, and we use a capital C for that. Now, we will cover this again. In the next video I put up, we're going to look at some example questions that involve these, so you'll see how these symbols and units are actually used in questions. For now though, this was just a wee reminder of what they are, okay? So, we've covered then the basic definitions of what current, voltage and resistance are, and then the symbols for using these. There's one other thing we want to look at before we move on to how these actually behave in a circuit, and that is your two different types of circuits. So you should have even built some of these circuits in S1 and S2, but when we're dealing with electronics, we can have series circuits or parallel circuits. So all electronic circuits can be split up into these two main types, series and parallel. Each of these circuits is built differently and they behave in quite different ways, so we need to know the difference between them. And this applies in S3, Nat5 and even on to higher, advanced higher. The difference between series and parallel circuits is really important, so this is something you definitely need to remember. So let's start with looking at series circuits. These are your more basic circuits. So this here is an example of a series circuit. Now there's two little diagrams here. These both represent the same circuit. This one on the left here just has pictures, so it's got a picture of a battery here. On this one we've used the circuit symbol for a battery. Here this one's got pictures of bulbs. Here we've just used the circuit symbols for these. Now remember, when we're drawing circuits, we use these circuit symbols that you see on the right to keep everything standardized, because maybe my drawing of a bulb would look different to yours, and then if a third person came to look at it, they might not know what either of us was talking about. But if we all drew this, the symbols you see on the right, then everyone knows what's actually happening in the circuit. The key facts to remember about series circuits are there is only one path in it. Okay, if you've got electrons coming out of your battery here, there's only one way around the circuit they can go. They pass through both the bulbs, then they come back in the other end of the battery, out the start, and repeat that over and over again. There's only one way between them. Okay. However, the voltage, that is the energy that's pushing them, that's split up between the components. So if I said we had 10 volts here, sorry for that, it's quite hard to draw on these, as this is being pushed around the circuit, okay, we come around here, it's using maybe 5 volts of that energy to push the current through that bulb. So by the time it gets here, it's only got another 5 volts left. Okay, so now there's no volts left. It's coming round, and when it gets back here, it charges up again, you can think of it like, and 10 volts come out again, come round, 5 volts go into here, 5 volts go into this one. Okay. Current though in a series circuit is the same everywhere. So if we get rid of this wee bit here for voltage, if we try to anyway, if we say there were 2 amps of current in the battery, okay, that means down here in this lamp there's 2 amps as well, and in this one there's 2 amps. So in a series circuit, wherever you are, whether you're up here, whether you're here or here, the current is always the same. This is not true for parallel circuits. Okay, so let's have a look at a parallel circuit here. Again, we've got 2 of them drawn. We've got one here with drawings and one here with the circuit symbols. Again, we've got a battery at the top, circuit symbol for a battery. We've got then pictures here of some bulbs. Notice these are different pictures of bulbs from before, but it's still the same circuit symbol, so you know what we're talking about. Okay, so in a parallel circuit, the big obvious difference is that the circuit has more than one path. If you've got something, your electrons coming out of the battery here, it gets to this point, your electrons could go this way and back into the battery, but they could come down here, they could also go this way and back into the battery. Okay, so for the parallel circuit, there's more than one way for those electrons to go. Doesn't just have to be 2, like in this picture here. Could be any, could be 100. Okay, it just has to be more than one way for the electrons to go. The other differences come down to how voltage and current behave in them. Okay, so whatever your voltage is here, so say it's 10 volts again. Now, that 10 volts is given to every branch. Branches are what we call these little different paths the current can take. So if you've got 10 volts here, you'll also have 10 volts here in this branch. And then again, you'll also have 10 volts there in that branch. Okay, so whatever your supply voltage is, it will be that voltage in each path of your parallel circuit. And now let's look at current, which again behaves differently to how it does in a series circuit. So before, where in a series circuit the voltage split up, in a parallel the current splits up. So let's say we had 2 amps like we did last time. That's the current up here present in the battery. As this current comes around, you're going to get it split up. So you might have 1 amp here in this lamp, and you'll have 1 amp there in that lamp. It doesn't have to split up equally, but it does have to split up so that all the initial current is accounted for. If these lamps were different from each other, and we said that this lamp here had 0.5 amps, that would mean that this one down here had to have 1.5 amps. So you'll see that the current has split up, but the 2 of them added together, the 0.5 and the 1.5, both still add up to what we started with, the 2 amps. So, just to finish there, difference between series and parallel. Series circuit have 1 path, parallel have more than 1 path. Okay, voltage splits up in a series circuit, doesn't split up in a parallel. Current doesn't split up in a series circuit, does split up in a parallel. Right, that's where we are going to finish today. Next video session, we're going to look at some examples of this and actually using the ideas of voltage, current and resistance in some equations and problems. But thank you for watching that, and you'll hear from me again soon.